Yeah. This is about graph. We're familiar with, right? In multivariable calculus. Okay. So given a set, right? This is a set U, okay? In XY plane. Then you have a function defined that. And the graph of the function is actually the graph of the equation z equals f of it. It consists of a point in the space, okay? And the third component, okay, is determined by the first two components. Okay? So you will get kind of surface as long as the function is smooth. Okay, this is a smooth surface. So at least we should get some idea what kind of surface look like. Okay. Like if the function is just not smooth, then the surface is maybe have some kind of singular points there. Okay. Yeah. Okay. So let's look at some examples. Okay. So when f is smooth, then the surface looks like a smooth function. There is no singular points on the surface. Okay. And there are two type of examples. One is f of x, y equals square root of x squared plus y squared. Okay. Now take a look at this. This is defined on the whole plane. Okay. It's on the u is again the whole plane. Okay. Then the graph is actually going to be cone. Okay, and this is a surface, but to you it's obvious, right? This is going to be a single point. It has a single point, right? So everywhere else, it's a surface nice, smooth, in the usual sense. And we are going to give a more precise definition. So this is a graph. So the graph of f is a surface, but we haven't defined what does a surface mean here. It's the surface in R3, okay? And there was a singular point, okay? 0, 0, 0. Right? Get some ideas about it. It's easy to understand the graphs. And then they look at another example. Okay. If I have this function, right? Okay, then this function is more smooth everywhere. It's not. It is an above function, square root of x squared plus y squared. This is not differentiable at its origin. Okay, that's why the graph is single in some sense, right? Yeah. So the f, okay, is not differentiable. It's not differentiable at the 0 and 0. Okay. So now this function, the graph of this is a surface, okay, in R3, and it's smooth everywhere, without single point. Okay, we're going to study surfaces without single point. And if there's a single point, you have to delete that single point. Then I'm going to introduce a notion of the curvature. The curvature is not defined as a single point. Okay, that's the whole point. You cannot talk about curvature. That's a single point. And the same is true for the curve, right? If there's a single point of a curve, you cannot talk about curvature at that point. It's not defined as curvature, right? And this is a paraboloid, right? Okay, it's a smooth. It's not like a cone. This is a cone-like surface, like circular cone. Okay, so this surface is smooth everywhere. So you can talk about geometric quantities at every point. Okay, and now let's look at the surface in slightly different way. Okay, I'm going to define a map. This is RU, which is R2. So just use the same example. I'm going to define a sigma from R2 to R3. Okay, okay, it's kind of map. Okay, X and Y is assigned to XY and X squared plus Y squared. Okay, so this is a map. Actually, the image, okay, it's a from, yeah, just look at this. This is my R2, right? X-axis and Y-axis, okay? Review that. So a point here, X and Y, is assigned to the point here. How can I get that point? Actually, you can look at the corresponding point, just go up. Okay, so if you separate this, let's just send it to here. Okay, so that's a called, yeah. So then the graph of F is the image of sigma, okay, right, in R3. Okay, so then you can get a map, right? So map is from R2 to R3, and the image is going to be the paraboloid. Okay, so this graph is covered by one single map here. Okay, but some surfaces we are probably cannot covered by one map. Yeah, in this case, yeah, we can say that the graph of F is covered by single map sigma. Okay, this map we are going to call it in the future is called a surface patch, something like that. Okay, this is covered by single a single map, not singular map. Okay, one single map. Yeah, one map. All right, you know, we can make it more precise in the future, but this is how do you do that? And the sigma is a vector value function, right? Sigma is vector value function. We understand the surface as an object in the three-dimensional space, and as the image of a vector value function. Okay, this is a vector valued multivariable function in two variables. Okay. Right, and this sigma has some nice properties. Okay, smooth, right? The first one. Smooth means differentiable. Okay, differentiable. Okay, as many times as you want. Second, sigma is 1 to 1. So it's not like get a self-intersection point. It's 1 to 1. Different points send to different points in the space. I think, yeah. More important, it has another important point. We're going to verify this later. Is actually, yeah, this we understand this later. Okay, this never be 0. Okay, as a partial derivative. This is I will explain the third point later. Okay, so those are the nice properties of this sigma. Okay. Now let's take a look at the example of the sphere. The sphere. So surfaces can be the sphere, yeah, the sphere like x squared plus y squared plus z squared equals 1. Okay. So now the sphere is a graph of this function, or it's called the level surface of a function. Okay. So the sphere, yeah, the sphere S, yeah. So S is S is a graph actually. It's also a graph, but it's not a graph of function. It's a graph of the equation, right? Or you can also view this as a level surface of this function. Now this function right now has 3 variables, right? Yeah, set f to be 1, then you get the level surface. In any sense, right? Whenever you're going to introduce what kind of definition you're going to introduce, the sphere should be called a surface in any definition. But you have to introduce some kind of abstract definition for the surface in a 3-dimensional space. How to define it, right? But this should be the surface, okay? And I'm trying to cover this sphere, right? This is sphere, right? In 3-dimensional space, X, Y, Z. And I have a piece of paper and some domain. I'm trying to find the map, okay? I'm trying to find the sigma. It's from R2 to R3, such that the image is a sphere. But probably I cannot make it like that. Topologically, they're quite different, right? You know, how can you hold a piece of paper, stretch it, bend it, and make a sphere? It's impossible. There are some singular points shows up if you do that, okay? You can use a disk, okay? How can I make it, right? Try this. This is disk, and from here to here is the height, right? The radius. Then you shrink right? Shrink it, and finally you make it like but there's a single point here, right? Okay. Yeah. Okay. You compress the top end, make the circle smaller and smaller. Finally, only get to 1 point. So this is an open set. So this point is never be covered because the North Pole is not covered. So I can find the sigma to cover the whole sphere as much as possible, but I cannot cover the whole sphere. The sigma must be 1 to 1. Okay, what I was trying to do is, trying to find sigma. It's from some open setting R2 into R3, okay, with the following property. One, sigma is smooth, okay? Second, C infinity means it's smooth, okay? Or differentiable as many as possible as a vector function. Second, right? 1 to 1. I don't want like a 2 points. There's 2 different points sent to 1 point. Okay, this must be 1 to 1. Okay, it's called the injective in sometimes. The third one is sigma x cos sigma y is not going to be 0. So that means why? Because the geometric meaning of this is this is eventually called a regular. Okay, but this is I will explain this probably later. And such that sigma covers, I put here a portion of that, right, of the sphere. Cover the sphere. I don't think I can cover the whole sphere. Okay, if imagine if I look at my picture sequence, right, go over from here to here, I think I can cover the whole sphere except for the North Pole if I want. Okay. Some are nature cover, the nature map probably not. Okay, only cover the semisphere, lower semisphere, upper semisphere. But if I use a different kind of map, maybe let's try it. Okay, how many sigma we can get? After getting familiar with this, then we probably can go back to the abstract definition of surface. Right? Yeah, let's do this. yeah, the geometric meaning of this sigma x, okay, is going to be like that. The geometric meaning is very simple. Right, this is a portion of sphere. So sigma x will be the tangent vector to that curve, right? And the sigma y will be tangent vector to the sphere along another curve. Okay, those two curves are determined by the curves. You see, here's the point. Okay, this is the domain U, right? So let me draw those two curves. One is the red line. Okay, so this is going to be the image of this. Okay, and then the I need to get another color, right? Yeah. Then I have this one. Then I get this. Okay. So this cross product not equal to 0 means those two are linearly independent. Otherwise, you will get some strange picture. You know, it's not like a nice. Yeah, you can use those two. Yeah, it's not collapsing something. Okay, it's not collapsing something. No single point. Okay, so that means these two are linearly independent. Okay. Linearly independent. Okay. So let's see, how do you find it? The very natural one, I think I can try this. Okay, I look at this equation and I solve this plus minus 1 minus x squared minus y squared. Okay, so that gives me the upper hemisphere, lower hemisphere will be graph of the two different functions. I call it f prime minus, okay, x, y. Okay, so the up hemisphere, okay, is the graph of f prime plus, okay, and then the lower hemisphere is a graph of f bar, f negative. Okay, now both f plus minus is defined on the so-called disk 1, okay, in R2, and it's map. Okay, this is defined on this. It's just a function on this. Okay, is a function. Yeah, is a smooth function on the unit disk. Okay, so this unit disk, x and y, x squared plus y squared less than 1. Okay, it's not equal to 1. Equal to 1, you have a single point here. So we only consider open side. Okay, so yeah, so I can get sigma plus minus, I have a 2 here, right? And this is going to be disk, send it to R3. The image is going to be sphere. Okay, so x and y, send it to sigma. It's defined x and y and plus minus. Right? So we find the two maps. Actually, we can have more maps than that. Okay, we find the two maps. Okay, and you can check. Yeah, these two maps. So the image is upper hemisphere, lower hemisphere. Okay, clearly, sigma this is a smooth, right? No problem, differentiable. Second, sigma this is 1 to 1, no problem. 1 to 1. Oops, I wrote too fast. The files are going to have trouble. Okay, wait. I probably have to reopen it. No, good. Coming back. Yeah. 1, 2, 1. Because it's 1 to 1 is because x1, y1 are not equal to x2, y2, then the image clearly is 1 to 1 because the first two components, right, will be different, right? Now the third one, we probably can also check that quickly. Let's look at that. Sigma plus partial derivative with respect to x. It's going to be 1, 0, plus minus when you differentiate about. I'm going to get I think I'm going to get negative x, okay? And then negative y. Right, then you look at the cross, clearly these two are linearly dependent, right? I don't even look at the cross product. Clearly they are linearly independent. Independent, okay? So it's good, it's nice, yeah, it is, this is pretty nice, right? Now you can cover the manosphere using how many of them? You can use 8, I think. 2. You have to 2 times 3, 6 pairs. Then every point is covered. Right now, you only cover the upper hemisphere, lower hemisphere, right? Yeah, you can cover upper hemisphere, lower hemisphere. Let's use a different color. Right, upper hemisphere covered like that. Lower hemisphere covered like that, right? Okay. Then we have a trouble with along this. This is not covered at all. Right. Right. So if every point on the sphere is covered by this kind of map, I have to define other maps, right? I can try this one. I still the sphere, but let's go this way. So you divide the sphere into 2 parts, but using the plane going through x, y, z, right? Instead of use the x plane, use the xz plane. If you use the xz plane, you will get this side is a yellow color, right? And the one on the other side will be this. Okay, then at least it's guaranteed point along this, right? From above, you cannot cover it's the points on the equator. Now, most of the points on the equator are covered by either this, by 2 of them, right? So I can use a sigma, I can use a sigma plus minus, okay? This is going to be to a disk. Actually, it's a disk, still a disk. Yeah, I'm going to, it's a map. Yeah, how do you define this disk? I use a variable x and z instead of xy. So that means it's going to be x is here plus or minus square root of 1 minus, you solve for y, okay? X squared minus z squared and z, okay? So as you can see that, yeah, this has similar properties covered. But you do need another pair because there's a point here. It's still not covered by any of this. Right now I have total 4 maps, right? 2 pairs of maps. And there's a point like is 1, 0, 0. right? That point is not covered by any of this. So you have to have use another one, okay? Another set, okay? Another set that would be okay. Another set, I think it's a YZ, okay? YZ. So it's going to be plus minus 1 minus y square minus z square and the YZ, okay? So now you have 6 maps, and then the images cover the whole sphere, okay? We can eliminate, okay? We can just have 2 maps, but we cannot have only one, okay? We can have 2 maps, but right now for the convenience, we don't need to find out as a, yeah, we just use these 2. Those are the standard one, okay? So we can say that sigma plus minus and cover the whole the sphere, right? Yeah, that is reason. For example, in order to get all the signals from the satellites, right? We cannot use one single satellite because the satellite does not cover the whole sphere. Only the upper hemisphere, lower hemisphere, for example. Okay, how many satellites you need? Make it as many as possible, right? But sometimes, yeah, so the same idea, right? It depends on what kind of mapping you're going to use. So geometry is used in many problems, okay? Space science, for example. Yes. Okay, so we get some ideas about this. Yeah, so sphere cannot be covered, cannot be image of one single vector valued function. Okay, was those 3 nice problems, most in one-to-one and linear independent. Okay, yeah, the sphere. But the others, yes. So roughly speaking, okay, roughly speaking, a surface, yeah, what is a surface in R3? Okay, here's the question. How to define it? What is a surface in R3? Okay, how to define it? Okay. Right, this is right. A surface in R3, roughly speaking, it is at every point. Okay, this is my def. Okay, at every point there's an open set which can be viewed as which can be viewed as a regular surface defined on the can be viewed as the image of above a map. Okay, so roughly speaking, okay, a surface S in R3, okay, a regular surface. So what's we consider, actually we just want to consider smooth surface. Okay, we don't want to, because we use what is the smooth surface. Okay, a smooth surface S in R3. Okay. Okay. Is a set, okay, in with the following property. Okay. So at every point, point P, in the surface at every point here. Okay. There is an open neighborhood, open set in R3. Okay. Open. There is an open set W in R3 such that this open subset could be like that, right? Such that W, right? Such that the intersection of S inside this W, such that this is the image of a sigma, okay, with the above properties. Okay. Okay. This sigma was a properties we already mentioned, was above property 1, 2, 3. Some open set to R3. Okay. Was above properties 1, 2, 3. We already mentioned. Okay. So I don't want to go through very technical details, like, but that is probably is good enough. So whenever you find like a continuity, regular map, but as long as this set in the space at every point, you can cut a small neighborhood, cut a small piece. That small piece is image of some regular, some nice map. Okay, sigma. Okay, so sigma is called parametrization of surface. Sigma is also called parametrization of the sphere. Okay, this is also called surface patch. Okay, surface patch. Yeah, it's called a regular, because we're talking about smooth, so regular surface patch. Okay. So every point you have, it should be covered like that. Every point there's a small neighborhood. Okay. Small neighborhood. So the picture is pretty clear, right? So this is like that, right? For example, this surface. So at every point, I can look at the domain W, and so the intersection is this part, and this should be the image of sigma of some open domain. Sometimes we use because since we have to use X, Y, Z, so we can use U and the V. Okay, so such that this sigma has a property 1, 2, 3, and this piece inside this domain, is the image of some sigma. Okay, then in order to study surface, all you have to do is using those special regular surface patches, right? And maybe there are multiple choices for surface patches and the relations. And I think okay. Now, clearly, given surface, right? It's covered by, because every point you can have this, right? So it's covered by regular surface patches, or right? Then they're not unique. I just want to say they're not unique. even for the sphere, we have many, we can define many surface patches for the sphere, okay? So let's go back to the definition. Our definition, a smooth surface, we only consider smooth surface. This is just a set in the three-dimensional space with the following property at every point P, there is a open set W in the three-dimensional space, such that intersection part is this part, right? This can be viewed as an image of a regular surface patch, okay? The regular means it has three properties. One sigma is 1 to 1, and the smooth as a function of the three variables. It is smooth and differentiable, right? You know, sigma is a function of it. Yeah, sigma is just a function of, if this is a u, right? Sigma is just u into R3. It's just a vector value function. Okay, so differentiable. Another property is that it's a regular in the sense that those two are linearly independent. Okay, let me repeat again. Sigma is differentiable, is smooth, differentiable as many times as you want, then you call it smooth, right? Second, sigma is 1 to 1. Third, sigma x, sigma y are linearly independent. Okay, so those are the three properties we want to keep. All right. So let's go back to sphere. I know I cannot find a single one, but we already find 6. Okay, 3 pairs of them to cover the whole sphere. Okay, so at some point, you can even have a multiple of regular smooth patches, regular surface patches. Okay, right? Yeah, let's go back to, it's not necessary to be unique, you know. Yeah, let's go back to the example. Let sigma plus minus, sigma to the plus minus, sigma to the plus minus, I don't have any notation. Okay, be function constructed as above. Okay, for the sphere. Okay, so let's see. Right, and then even just North Pole, right? And which regulars are all regular surface patches, okay? So which one cover that point? Okay, clearly sigma plus, right? Okay, yeah, sigma plus and cover them because it's in the upper hemisphere. I think every point here one in the front, the other one in the back, or left, or right. I think that this particular coin is only covered by one page. Okay, if you look at the one on the, if you look at the one on the right, one on the left, right? Okay, then it cannot cover, does not cover, this one does not cover the circle in the XZ plane. This one does not cover the circle in the YZ plane. Okay, so only one, okay, cover this point P. Okay, but there are other points covered by multiple of regular surface patches. Somewhere here, you know, it's belong, yeah, it's covered in the image of several regular patches. But this particular point is covered only by Yeah, no, this point only by sigma times, yeah, point P. But other points covered by multiple of regular surface patches in the above set. Okay. So I'm going to try another one, construct another one. Here's another. Right. Okay. I just need two. Okay, this is a sphere. Okay. I put plane on the top, attached to that. Okay. How can I define the map from here to here, right? How can I define the map? Okay, this is another way to define. Okay, here's a point, upper hemisphere. Okay, this is a point, right? I want to find the map, some point here, right? How can I do? This is the center. I draw the line, a straight line going through the surface. And here's a point. The coordinates of this point is x, y, and the 1, right? Because this is in the plane. Right? So how can I define the sigma? I call define sigma top, right? I take an arbitrary point x and y. I go first, I go to here. I just add the 1 to the component. Then I draw the line and go into here. Okay. This is how do we get the map. Okay. So let's find out the formula. Okay, this sigma is not from the disk. It's from R2 to up to the up hemisphere. Okay. It's different from the one above. And the above one is defined from the unit disk to the sphere, right? Okay, so let's find out. How can I do that? Well, it's very simple. I just need to make sure this vector, right, is on the sphere. So the difference between x, y, and the 1 minus the origin, right, multiplied by lambda, this should be on the sphere. Okay, I just needed to determine the lambda. So I look at lambda is positive, right? So it's a square of x squared plus y squared plus 1 should be equal to 1. So that means lambda should be equal to, okay. So I got my map. This is a lambda x, y, 1, right? So sigma x, y is going to be lambda x, y, 1. So it's going to be that, okay? And you can check this map. Indeed, is a regular surface patch, okay? Sigma is a regular surface patch type 4S2. Regular means by definition it's a smooth and 1-to-1. It's a smooth and 1-to-1 and sigma u sigma x sigma y not going to be linearly independent. Yeah, the surface patch by definition must be 1-to-1. Okay. So you can verify that, and this is indeed regular. Okay, it has the following properties. 1, right? Sigma is smooth, no problem. 2, sigma is 1-to-1. Okay, so these two conditions already implies called the surface surface patch, okay? A smooth surface patch. It's not called regular, okay? It's called smooth surface patch. And then at a certain condition, then it's called a regular, okay? So this is called a regularity. Okay, it is this condition. But so we do have another, you can define another one. This is the top, right? So similarly, you can define the bottom one's -1. Now then sigma negative x or y. Right? So this, this two does not cover the whole sphere, if except for the equator. Okay. Okay. So these two do not together, okay, cover the sphere except for the equator. Okay, do not cover the whole sphere. Okay. The reason is, if you have a point, right? If you have a point, right, on the equator, you're not going to never, if you draw the line from the center with a point nearby the equator, then it's very far away. Here, it's too far away, right? And if the point is on the equator, the line you're going to draw from the center to that point will be parallel to the tangent plane on the top. So it's never intersecting tangent plane. Okay. If we really want to find the one which cover almost the whole sphere, with a one exception point, here's another way to construct. Okay, construct another one, sigma. Okay, so this time I'm trying to cover the whole sphere except for one point. How can I do that? Okay, this is again this picture. Okay. So I choose this point instead of a center. I draw the line. Okay, I'm pretty sure. Yeah. So this is a map. X and Y is a center to here first, then draw the line to the source point. Okay. Then you get the intersection point. But that intersection point can be anywhere in the sphere except for the source point. Okay. So this is the point. That's the image. Okay. So let's figure out what is that. Okay, we can find the formula. Okay. So this is going to be here's x, y, and the 1. So actually, this is a map my sigma, right? Let's find the formula for this. All right. I said there are many ways to parameterize this sphere. We call it parameterize the sphere. Okay. You cannot parameterize the whole sphere, but you can parameterize most part of that. Okay. So what I want to say, first of all, the image of sigma plus is going to be the whole sphere minus the source pole. Source pole is 0, 0, -1, I think. Yeah, you need to that, right? So there's whole here. I cannot cover the whole, so. So let's find the formula. How can I find it? So this point 0, 0, 1. Right? So how can I determine that point? I can, arbitrary point on this line can be defined, yeah, sigma plus xy can be the combination of these two. I can say t 0, 0, 1 plus 1 minus t x, y, 1. How about that? All I have to do is determine the value of t, right? Because when t equals 0, you get a source pole. When t equals 1, you get a source pole. When t equals 0, you get you get that point. So you just need to determine, yeah. So you determine the value of t. So I get 1 minus tx, 1 minus ty, and I think 1 minus, here's 1 minus t minus, I think it's minus 2t here, right? There's a negative t here. I have a 1 minus, yeah. That's making it a little bit complicated. Instead of, I'm going to use, I'm going to change the variable here. Just t, this is a 1 minus t. Okay. 1 minus t and the t, okay? So save me some. So I get tx, ty, t plus 2t minus 1. Yeah, that is better. Okay, so now it's on the sphere, so the length, right, should be equal to 1. So I get t squared x squared plus t squared y squared plus 2t minus 1 squared is going to be 1. All right, so let's try to calculate. It's t squared x squared plus y squared plus 4t squared minus 4t plus 1 equals 1. So this 1 canceled out. Actually, you also canceled out the t. I think I'm going to get a t. T is a 4 x squared plus y squared plus 4. Okay. So that's it. So then I put back sigma plus xy. I'm going to put t here to 4x. Okay. And here 4y. And the 2t minus 1. Let's say 2t minus 1 is going to be what? 8x squared plus y squared plus 4 minus 1. So 8 minus 4. 4 minus x squared minus y squared. Okay. So that's the map. You find out. It's complicated, but it's it is indeed a map described about the image. Now, much harder to compute. It's 1-to-1. It is a regular. Okay, it's a regular. Yeah. So this is a regular surface patch, and it covers the whole sphere except one point. That's very good. Okay, this one covers the largest area compared to other previous constructions, regular surface patches. right? And you can have another one called sigma negative, right? And then it can cover the whole sphere with except for the north pole. Right, let's continue. Yeah, consider the cylinder, circular cylinder. Okay, x squared plus y squared equals 1. It's determined by this equation. It's in three-dimensional space. Okay, this is cylinder, right? It's clearly, in any sense, it should be a sphere. Should be a smooth sphere. Okay. And without single point. Our job is to find regular, yeah, we're trying to find a regular surface patch. Okay. And I don't think we're going to cover the whole cylinder. Right? Find a pair of regular surface patches, okay, to cover the whole cylinder. That means the image covers the whole cylinder, okay, to cover the whole cylinder. Okay, let's do it. Right, how to do it? I define a map, and I'm going to call it theta. And let's call it t. Okay, so theta, this is cosine theta, sine theta, and the t. That's it. Okay, so sigma is from R2, no restriction on theta, right? Into R3. Okay. What do we see? Okay. What do we see that it's first of all sigma is a smooth, no problem. Second, sigma is 1-to-1. That's a question. Okay. However, sigma is regular. Okay. Sigma is regular means sigma theta cos sigma t is not greater than 0, or they are linearly independent. So we can check the last one. Okay. Right, so let's look at. Very interesting. So clearly they're linearly independent. Okay, so clearly sigma theta, sigma t are linearly independent. Okay. Now sigma theta sigma t, the cross product is not given 0 if only if they're linearly independent. Okay. Because they're linearly independent. That's all we need. Now, I think the image of the sigma is a whole cylinder. That's no question about it. The only problem with sigma is not one-to-one. I can do the following. I let sigma to be sigma 1, I let sigma restricted to from 0 to pi. Okay. Okay. Instead of a whole line, just from 0 to pi. Another one, sigma 2 from half pi. Wait a minute. It's a whole circle. I think it's, I need a 2 pi. Okay. Yeah. So I shift a little bit. 2 pi plus half pi. So So 2 pi, okay, here's 2 pi. This is, look at thing. 2 pi is from here all the way to here, except for that, right? Cylinder cover this, okay, this is from, yeah, okay. And from pi to pi over 5, this circle. So then I think it covers, or you can change it to pi to 3 pi, it's not a big deal, okay? You can rotate, you know, I say, okay, pi to 3 pi. Then in this case, it goes like that. Okay. So theta is between pi and 3 pi. This here, theta between 0 and 2 pi. Okay. So the image of sigma 1 is the whole cylinder except the vertical line. Okay. So both are here, sigma 1, sigma 2 now are 1-to-1. No question. Right? It's easy to see. Right, from the difference. And what is the image? The image of sigma 1 is the whole line, is a whole cylinder. Okay, except the vertical line. Determined by x equals 1, y equals 0, z equals t. Okay, then similarly, the image of sigma 2 is a whole cylinder except for the vertical line. X equals, I think it's x equals -1, y equals 0, z equals t. Okay, so let's look at the picture here. Yeah, this is a broken here, right? And here's, no, I did not draw correctly. I needed to redraw it. actually this line, right? Okay, this line is deleted. And then the other one, okay, the other side is, okay. So this side, this line is missing. The reason you cannot cover the whole ceiling is because otherwise they're topologically the same, right? But the topology is similar, same as a plane. The plane is a topologically is trivial. The cylinder is not. Okay, that's the reason you cannot have. You must have at least two regular surface patches to cover the ceiling. Okay. So I needed to talk about the transformation a little bit. Okay. So you have a abstract surface. Okay. Then I have two maps. Okay. This is a X, U, and the V. So that covers this region, sigma. Okay. Yeah. Both are. Then I have another part. Okay. This is going to be UV, U prime, V prime. Okay. So what happens in the intersection area? Right? Intersection area, because this is a one-to-one, right? Both sigma prime are regular surface patches, okay? for S. Okay. We can show that at least, okay, this area, this is a common area, right? This is a common area. So what happens to this common? So coming from here, also come from here, right? So we are going to have a map from here, depends on how you define. Okay, so this is a U, a V, right? So what I'm going to do is I'm going to send it to here. Then I pull back to here, okay, by this sigma. So I can define first one is sent by this. Yeah, I'm going to use a tilde instead of right. Then you pull back. This is it's invertible, right? The map. So what you get is you get a map. Right. So it's get map from some set in U2 to U1. Okay, some set. Okay, not the whole U. U2 then to U. Okay, so it's such that. Okay, right. You can also reverse this procedure to, yeah, what is this? What is this? Phi, the inverse. It's a one-to-one, right? So this is you can have a map from here to here, so called phi. And then reverse it called the phi inverse. So actually, the inverse is going to be defined by that. So therefore, so we here's a few facts we have to say that this phi are smooth, okay? Must be smooth. And it is also another fact, important fact is the so-called Jacobian, okay? That's first property. Second property, the Jacobian is going to be it's going to be regular, okay? Is regular. Okay, what does that mean? Jacobian is regular. This Jacobian is defined by okay. So here we denote by this, okay? So UV are function of U2 V2. And then this is a determinant is not going to be zero. So I'm not going to go through that, but this is suppose you have two patches. Suppose you have two patches, regular patches, and then you get the map between these two open sets, portion of these two open sets. And this map is a one-to-one is clear, but from definition, because sigma 2 are both one-to-one. Then there must be differentiable, and then the Jacobian is regular. That means the determinant. Yeah, the determinant of this is not going to be zero. Okay. Right. So that's the relationship between two regular surface patches. We probably can discuss this later in another class. Okay, so let's stop here.